All right, in this video we're going to focus on conservation of energy problems. In the last video you learned that there are two different types of problems that we're going to be solving, conservation of energy problems and work problems. So just as a reminder, remember it's a conservation of energy problems if there is no work done by non-conservative forces. So anyway, in this video we're going to focus on how to solve those problems. And the cool thing about them is once you learn how to solve one of them, you can solve any of them. They're a little bit tedious, I guess, but once you learn how to solve them, it's just the same thing over and over and over again. All right, so here we go. Here's the law of conservation of energy. It says energy cannot be created or destroyed. Energy can only be converted from one form to another, like from kinetic energy to potential energy or vice versa, or passed from one object to another. All right, and the bottom of this really solidifies what we're going to be doing in this video. What this means is that as long as energy is not passed from one object to another, in other words, if the non-conservative forces don't do work, an object's total energy will always remain constant. Okay? So, total energy will always stay constant if the non-conservative forces don't do work. So it's probably worth reviewing. When does a force not do work? So, let me do this. Okay, so how do you know if a force does no work? Well, a force does no work if either of these two things are true. Either the object isn't moving, or the direction of motion is perpendicular to the force. All right, remember like the cat, where Carl was carrying the cat, right? So here's the cat, right? Cat's moving this way because Carl's carrying it. The only forces on it are gravity and Carl. Both of those forces are perpendicular to the motion, so neither of those forces do work. Okay? So that's how you know if a force does no work. So now, having said that, if that's true, if your non-conservative forces are doing no work, then your total energy is constant. And so what that means is that the total energy that you begin with is the same as the total energy at some later point. Okay? Your total energy stays constant. That's what is true in a conservation of energy problem. Okay? So let me show you a quick example of that. I'm going to try to use this little applet here. Oops, that's not what I wanted to do. I wanted to do this. Cool. So in this example, we've got this skateboarder, right? Okay, and you can see he's hanging out up here at the top of the ramp, right? And because of that, if you look, oh no, I always do that. If you look over here, ignore this red line, you can see that the dude has a lot of potential energy, right? Why does he have so much potential energy? Well, because he's way up high, right? Okay. Now, the only two forces on him are gravity, which is a conservative force, all right? The only non-conservative force is the ramp. And it turns out that the ramp is what's sort of supporting him, right? And so that's a normal force. So remember, in this class, for all intents and purposes, the normal force is always, that didn't work. The normal force is always perpendicular to the motion, and so it doesn't do work. All right, so probably easier to see. Let me hit go, and you'll be able to see it a little bit better. So boom, boom. All right, so what I want you to do is, as the guy is rolling, watch this graph over here, okay? All right, so here we go. All right, so what happened there is as he rolled down the hill, his potential energy decreased, right? And in return, the kinetic energy increased. But the total stayed the same. So here we have an example where we just converted energy from one form to another. In this case, we converted potential energy to kinetic energy. All right. So let's talk about the forces on the object. Okay. So there used to be a way to bring the skater back. Okay. So you can see at this point, for example, that the skateboarder's moving, right? He's going to be kind of moving this way, right? And as a result, he's got kinetic energy. According to the graph, he has this much kinetic energy. He's still up some height, so he's going to have some GPE, right? according to the graph, he's going to have this amount, and the total energy is those two added up, which gives you this yellow bar over here. All right. So, but let's talk about the forces. All right. So the green arrow, well, let me erase this and do that again. So the green arrow represents the direction of motion, right? Okay. Gravity is going to pull the guy straight down, right? All right. Gravity's doing work because the velocity, the green arrow, the velocity, the green arrow, is not perpendicular to the force of gravity. So gravity does work, okay, which is less important than the fact that there's one other force, the normal force. But the normal force doesn't do work because it's perpendicular to the velocity. Okay, so Fn does the normal force does no work because it's perpendicular to the motion. Okay, so that's this fact right here is what identifies this problem as a conservation of energy problem, and it's what tells me that this total energy is going to be constant. Okay, so the idea is whether my skateboarder is up here at the top of the ramp, here halfway down the ramp, or all the way at the bottom of the ramp, the total energy is constant. All right, so let me play the video one more time so you can see it again. Let's take the dude, move him back up to the top of the hill. Okay, so right now the total energy is identified by this yellow bar. The potential energy is the blue bar. Notice there's a pie graph up here that's all blue. All right, let me do this in slow motion here. Kaboom. And let's watch him go down the hill. As he goes down the hill, look what happens. We get more green. We're getting more kinetic energy, losing potential energy, but he goes faster and faster and faster, and so the total energy stays constant. Okay? The same thing is true on a ramp that looks like this. Let's put him up at the top of the hill here. Okay? And hit go. He goes down the hill, he loses potential energy and gains kinetic energy. You can see the speedometer shows him going faster and faster and faster, faster and faster and faster until he gets to the bottom. Now he slows down as he goes up the hill. And now he's gaining potential energy but losing kinetic until he stops. All his energy now is potential. Now he comes back down the hill. The potential turns back to kinetic. And if I turn this on to normal, this will just continue forever. Okay? Now, in the real world, there would be friction and he would slow down, which is what this red energy is over here, the thermal. That's heat energy, which would be created by friction. Okay? All right, let's do this. A lot of times, your shape is more complicated than this. In a minute, we're going to look at a roller coaster, which is sort of like this, right? So here's my dude. Still works, right? Total energy is constant. All right? And in fact, if you pick a point, say the dude is right here, at any of these 3 points, they're all at the same height, so the potential energy is the same. His kinetic energy should be the same. That means at all 3 of these points, since he's got the same height, he's also going to have the same velocity. That'll become a little bit clearer as we go on. Okay? Cool. I was going to ask if you have questions, but this is a video, so I can't answer them anyway. All right. So there we go. That's the concept. All right. So, boom. Let me clear this up. Oh, I guess I didn't even need to do that. Next slide. All right. So let's do an example with some actual calculations. All right. So here we're going to drop a ball off a roof. Okay. And you're given the height of the ball at the top of the roof. It's 12 meters. And the question is, what's the velocity at the bottom? So the first thing is to identify this as a conservation of energy problem. The only force on it is gravity, which means that there are no non-conservative forces, which means there are no non-conservative forces doing work. Okay? So our total energy has to be the same. So what that means is that when the ball is at the top, it's going to have some total amount of energy. It has to have the exact same total amount of energy when the ball hits the ground down here at the bottom. Okay? So here's what we're going to do. We're going to find the total energy. So at the top of the path, we know the height, right? Height determines gravitational potential energy. So I can use, this information to calculate my GPE. I'm just going to do mass, which is, oh, I didn't give you the mass of the ball. All right. Technically, you don't need it, but whatever. Let's suppose the mass of the ball is 2 kilograms. So you're going to take the mass of the ball, you're going to multiply it by the acceleration of gravity, which would be 10 meters a second squared, and multiply it by the height, right? I'll write it out this one time. So it's going to be 2 times 10 times 12 is going to give you 240 joules of GPE, right? Okay. Now, because he's dropping it, that means the velocity at the top is 0, right? Before he lets go of it, it's not moving. So that means the kinetic energy, which is 1/2 mv squared, since our velocity is 0, our kinetic energy is going to be 0. So we can add those two numbers up to get our total energy. 240 plus 0 is 240 joules. So what that means is, initially, at the instant the dude drops the ball, this is how much energy it's got. Right? Now, there are no non-conservative forces here doing work. And what that means is, when the ball gets to the bottom down here, the total energy still has to be 240 joules. Okay, so let's write that down. That's huge. That means the total energy final at some later point, in this case, as the ball hits the ground, the total energy still has to be 240 joules because it's a conservation of energy problem. And we want to find the velocity. Well, the velocity depends on the kinetic energy, right? So if we can find the kinetic energy, we should be able to find the velocity. All right? Well, let's see. What's the GPE right there? Well, at this point, isn't the height 0? So since the height is 0, that means the GPE is going to be 0. So if my GPE is 0, but my total is 240, then by subtracting 240 minus 0, it tells us the kinetic energy has got to be 240 joules, right? It's the only way that it would add up to give you the same total energy. And now that I know that kinetic energy, now I can find my velocity. And plug in your numbers. So 2 times 240 joules divided by your mass, which is 2 kilograms. Don't forget your square root. Oops. And it gives you 15.5 meters per second. Okay. So, I guess a couple things about this. I want you to notice how I set this up. And this is something I'm going to be looking for you guys to be doing also, which is this. There's 2 points in the problem that are important. There's the point at the top. And all of the information that pertains to the top, I wrote at the top. Okay? All of this pertains to the top of the path, right? And then completely separately, and I even did it in a different color, down here, I wrote down everything that pertains to the bottom. That is a great way to keep your information organized. Okay? And the only thing that connects these 2 points, is that the total energy at the top has to be the same as the total energy at the bottom. Again, because there are no non-conservative forces. Okay? So, that's a cool problem. I know you guys are probably pretty fired up about it. But we could have solved it using some old equations, right? Because we know the displacement would be negative 12 meters. So we actually could use some equations from our first unit to have solved this. All right, so what about this? What if I gave you a roller coaster? This is something we've never done before. And even, I don't know there. Okay, so we've got kind of the same situation. So here's what we know. Up at the top. Oh, I don't want to do that in red because we already have red. All right, so up at the top, we'll use blue to represent the top. Up at the top, we know how high up the dude is on the roller coaster. We know his velocity, and we know his mass. Okay? And then the question is, down here at point A, at the bottom of this first hill, if he's 10 meters up, then what's his velocity when he gets to the bottom of the hill? And then part B is this. At the top of the second hill, what does his height have to be if he's moving at 25 meters a second when he gets there? Okay? So again, there's only really 2 forces on him here. There's gravity pulling him down, which is conservative, and the normal force, which remember, the normal force doesn't do work because it's always perpendicular. All right? So that means that in this problem, at all 3 of these points, up here at the top and at points A and B, our total energy has to be equal. So this is a conservation of energy problem. Okay? So let's use that. In order to do it, your first step is find your total energy. So I'm going to use the height to find my GPE. So you just do mass times acceleration of gravity times height. So these are actually going to give me some pretty big numbers. I think it gives you 40,000 joules. Okay. Kinetic energy, I'm going to do half of the mass times the velocity squared. Gives me 625 joules. I can add those up and get my total energy initially, which is going to be 40,625 joules. All right? That is huge, because now I know when I get down here to part A, where do I want to write this? I know that my total energy here at point A also has to be 40,625 joules. Okay? So what else do I know at point A? Well, at point A, I know the height, so I can use that to find my GPE by doing mass times acceleration of gravity times height. So that's going to give me 5,000 joules. So if I know my GPE at point A and my TE at point A, I should be able to find my kinetic energy at point A, right? Because they have to add up. So we're saying 5,000 plus what equals 40,625. So it's got to be 35,625 joules. Right? That's the only way they would add up. I just subtracted. Okay? So now that I know my kinetic energy, I can find my velocity. By using that guy. And you end up getting, oh, why doesn't my pen want to work? There we go. You end up getting 37.7 meters per second is the velocity at point A. Okay. All right. So now at point B, same idea. At point B, here's what we know. We know the total energy at point B has to still be 40,625 joules. Because we know the velocity, I can find my kinetic energy, which is going to be 15,625 joules. Okay, I just did 1/2 mv squared again, which means now I can find my GPE, right? Because these have to add up. So it's what number plus 15,625 equals 40,625. So it's got to be 25,000 joules. And now that I know the GPE, I can find the height. So I know my GPE is 25,000. I know the mass is 50. I know the acceleration of gravity is 10. So it gives you, oh, dang it, 50 meters. Okay, and that's how you solve those problems. The biggest mistakes I see people making are organizational. So please, please, please try to keep your information separately. You might even consider making a chart, you know, so that you keep all of the stuff for each point in one part of the chart. Okay, cool. I'm over my 20 minutes. Have a good day.